Hi, welcome back to Calculus. Today we're looking at section 9.4, which is comparison tests for infinite series. So we're going to be working here with theorem 10. Only one theorem to work with here. Oh no, that's not true. There's one more. Sorry, one more kind of comparison test. Theorem 10, the comparison test. We have three sequences, A sub n, C sub n, and D sub n, or three series rather. Let those be series with non-negative terms, and for some n, so if you go far enough out into the three series, the terms in the D series are smaller than the A, which are smaller than or equal to the C's. So we've used D and C here because they're going to stand for diverge and converge for us, and as a way to help us remember this. Basically, if the sum of the CNs converges, since C is the biggest one, if it converges, the sum of the ANs also has to converge. And if the sum of the DNs diverges as the smallest one, if it's getting too big to add up, then the A sub n's also have to diverge. So I have a couple of examples here. Let's look at this first one here. We can see it just fine. So we have the sum of n equals 1 to infinity of 7 over 7 n minus 3. So anytime you just have your only n is on the bottom, it's probably not a bad plan to try and make a comparison with a harmonic series. As we saw in the last section, a harmonic series is divergent. So let's see if we can make it work. 7 over 7n minus 3. If you factor 7 out of the top and the bottom, you get 7 over 7 times 1 over n minus 3/7. But the 7's drop out because that's just 1. And so we're left with 1 over n minus 3/7. And here's the thing. Since we're subtracting 3/7, that means my denominator is smaller than just 1 over n. But if the denominator is smaller, that means that as a fraction, it is bigger, right? A half is bigger than a third. So we can make a comparison here with the harmonic series, 1 over n. We know that that diverges because it is the harmonic series. And so because then we have a divergent series with our terms being always bigger, then our series has to also diverge. All right, let's look at this one. And I think we can see this as well. So the sum n equals 0 to infinity of 1 over n factorial. So remember, n factorial just means you multiply the first n numbers together. So 0 factorial is just 1, so 1 over 1 is 1. 1 factorial is also 1, so again we get 1, but then we get 1/2, because now we have to do 2 times 1. Then we have to get 1/6, because we do 1 times 2 times 3, which gives us 6. And so if you just keep multiplying the bottom here, you multiply by 4, then by 5, by 6, and so on to get these fractions. And what's nice is we're multiplying by numbers that keep getting bigger and bigger and bigger and bigger. And so we can make a comparison then with a geometric series. Because in geometric series, we keep multiplying that denominator by the exact same thing every time. All right, so let's take a look. I'm using 1 plus the sequence of the series n equals 0 to infinity of 1 over 2 to the n. I need that extra 1 because I have this 1 out front, right? I have 2 1s there. So if n is 0, I get another 1. And then 2 to the first gives me 2, 2 squared gives me the 1/4, and so forth. And importantly, at every step of the way here, each term is greater than or equal to the terms of the sequence that we're trying to compare to. Right? A half is equal to a half. A fourth is greater than a sixth. An eighth is greater than a 24th. And that will continue to be true all the way out. And so since we have a comparison with a convergent geometric series, where all of our terms are smaller than that kind of convergent series, then our series also has to converge by the comparison test. All right, next page, we're going to do the limit comparison test. All right, so let's look at the limit comparison test. The limit comparison test says, let's say we have two sequences that are both always positive, and that's for all n after some point. We really only care about the tails of these series. So we have 3 parts here. If the limit as n goes to infinity of a sub n over b sub n is equal to a number that is greater than 0, then either both series converge or both series diverge. If the limit as n goes to infinity of a sub n over b sub n is equal to 0 and the sum of the bottom terms converges, then the top also has to converge. The sum of the a sub n's converge. And finally, if the limit as n goes to infinity of a sub n over b sub n is equal to infinity, and the sum of the b sub n's diverges, then the sum of the a sub n's also diverges. All right, let's take a look at a big monster of an example. I want to look at this sum from n equals 1 to infinity of the square root of n plus 1 over n squared plus 2. All right, so we want to figure out if this converges or diverges. We need something to compare it to. So given the fact that we have a square root, a natural comparison here might be the sum of 1 over the square root of n, which is important because that's equal to the sum of 1 over n to the half, which is a divergent p-series. So we looked at that back in chapter 8. But we have a base being raised to a power, and since the power is less than 1, it's going to be divergent. All right, so we have a divergent series, which means either we're going to be using part 1, both converge or both diverge, or we'll be using part 3. Okay, so if we can make it fit to one of those, then we're going to be great. So let's take a look. I want to evaluate this limit, the limit of the square root of n plus 1 over n squared plus 2 over 1 over the square root of n. Right? That's what this whole theorem is about, taking those individual terms and evaluating the limit as n goes to infinity. Well, dividing by 1 over n is the same as multiplying by n, or sorry, 1 over the square root of n, the same as multiplying by the square root of n over 1. So I did that here. And then because we have square roots, I can bring this n inside the square root. But notice it's only going to the top, so n times n gives me n squared and then plus n. So I have this limit as n goes to infinity of the square root of n squared plus n over n squared plus 2. Sure, it would be nice if that square root was out of the way. Well, we can pull it out of the way because the square root function is a continuous function as long as n is greater than 0, strictly greater than 0. It's not continuous at 0, but we don't need to worry about that because we're starting at 1. So it is a continuous function. We can pull that outside of the limit and take the limit of the inside. And then I'm just going to divide all 4 terms by n squared, the highest power of n that we have. And what that leaves me with is that the 2 fractions at the end, the n over n squared goes to 0, the 2 over n squared goes to 0, because the powers on the bottom are bigger than the top. We know those go to 0. And the other 2 just turn into 1. So we basically get the limit as n goes to infinity of 1 over 1 inside the square root, and that all equals 1. And so since we got a number, we're going to use part 1. 1 is greater than 0. We know that they both converge or diverge, and so since we have a divergent p-series that we're making the comparison with, our series also has to diverge. So there we go. That was fun.